Hello everyone, I am Kabir. Today I am here with my two teammates, Mahendra and Abhishek. Today I am going to interpret the two problems that have been assigned to us and also touch some basic concepts that are going to be used in them.
Hello, I am Mahendra. I am going to solve the two parts of the problem number 2. First part asks us to generate a three address code for the given expression of A equals to B minus C star B plus C. Before solving it, let's get into a detailed overview of what three address code really is and why is it relevant. Three address code is a compiler generated intermediate representation of the high level language code, something like that. Uh, It consists of at most three operands, of which one is a destination operand and the other two are source operands. It's relevant because it converts the complex set of instructions into simpler set of instructions by using temporary variables.
Problem 2 asking from us. In this problem, we are given some arithmetic expressions where F stands for format, E stands for expression, T stands for term, and A, B, C, D are just some random variables stored in memory. And S is the assignment statement from which any process that we do, like generating any code, we start from there. In the first part, they are asking us to generate a three address code for the given expression. This A is equal to B minus C into B plus C using temporary variables. In part B, they are asking us to generate a RISC machine code for the 3AC obtained in A part above with load, store, which are data movement instruction, and add, sub, mul, which are arithmetic operation instruction. The data movement instruction has one memory operand and one register operand, and arithmetic operation has three register operands, one for destination and two for source operands.
So now let's sort out the three address code for the given expression by using the temporary variables. Here the temporary variables stores the data. So here the values to be stored are B minus C, B plus C and their product. B minus C star B plus C, which is A. So now clearly we have to introduce three temporary variables, which stores the value of B minus C, and the other one stores the value of B plus C, and the other one stores the value of that product, B minus C star B plus C. So now let's introduce the first one, say T1. So T1 takes the value of B minus C. T2 takes the value of B plus C. Let's introduce T3, which takes the value of T1 star T2. And finally, we'll assign T3 to A. So this completes the three address code generation for the given arithmetic expression. So there it is. So there it is, clearly the three address code, where C and B are source operands and T1 is the destination operand as said before. Similarly, that happens in the second one also. T2 takes the value of B plus C, and finally T3, which takes the value of the T1 star T2, and finally assigning T3 over to A completes the three address code generation for the given arithmetic expression. So now let's jump into the second part where we are going to generate a machine code for the above three address code. Here the machine level language is the low level language which is directly understood by the computer. So here in the above expression we have three variables A, B and C. Basically the variables store the data. So now for performing this arithmetic operations we need to bring that data into the registers. So for bringing the data into the registers, we introduce an operation named as load, which will be copying the data from the variable that's from the memory into the register. Uh, so now in order to store the data, in order to copy the data from B into a register named R1, we'll write it as load R1 B. Here the sequence really matters because it specifies from where the data has to be copied and from where it has to be and to where it has to be transported. Like load R1B specifies that the value stored by B has to be transferred into R1. Similarly, load R2C specifies that the value stored by C is stored into R2. And now, for computing the value of T1, which is equals to B minus C, we'll introduce an operation named as sub, which stands for subtraction, and is stored in R3. Here the subtraction is done. Here, since the R2 is subtracted from R1, we'll follow the sequence such as R1, comma R2, which specifies here also the sequence is really important because R2 is getting subtracted from R1. So we have to keep in mind that whichever comes first, whichever comes last will be subtracted from its further one. And now for adding, and now for computing the value of T2, which is the summed up value of B and C. So we need to add the value in the register R1 and R2. So we need to introduce another register which stores the value of the sum of B and C. That's the computed result of T2. So let's introduce the operation add. And since we are storing it in a register named R4, so let's introduce R4. And since it's the sum of the value stored in R1 and R2, so let's write R1 and R2. Here the sequence really doesn't matter because the operation of addition is commutative. So now finally, there is another temporary variable in the tree address code generated above, which stores the product of T1 and T2. So we need to bring another register, which name say R5, which stores the product of T1 and T2. That's the computed value. That's the computing of T3 here is done. So now let's introduce the operation mul, which is multiplication, and it's stored in R5, and it's done in between R3 and R4. So finally, there is another variable in the memory uh, to which the T3 is assigned to. That's the product of B minus C star B plus C is assigned to a variable named A. So we are going to copy the memory from the register to the memory to the variable A. So we are going to introduce a operation named store, which does the reverse as done by the load. That's store takes the value from R5 and stores it in A, which is in memory. And finally, the assignment of the T3 is done, and the total computation process has been completed. So this is how this is how the machine code for the three address code actually is, and this is how the computer actually works. Thank you.
We are solving the problems from set 6. So the first question is, you are implementing a signal processing algorithm that uses 8-bit 2's complement arithmetic. Three data samples need to be processed. X is equal to minus 120, Y is equal to minus 10, and Z is equal to minus 80. Your task is to represent these values in the processor's 2's complement binary format and determine which arithmetic operations will trigger overflow flags during execution. So, what is 8-bit 2's complement format? In 8-bit 2's complement format, we represent a decimal number in 8 bits, in which the leftmost bit is known as MSB, most significant bit, most significant bit, and the rightmost bit is known as LSB, least significant bit. The MSB represents the sign of the number. For example, if we have a positive number, the MSB will be 0. If we have a negative number, the MSB will be 1. And the rest of the number represents the magnitude of that number that we have represented in binary format. In this 8-bit 2's complement format, we have total 256 combinations leading to 256 different numbers, which range from minus 128 to plus 127. So if we add up any two numbers, for example, if we take 150 and 25, which leads to 140. And as you can clearly see, 140 is not in this range. So in this situation, we term it as overflow. If the number we got after adding or subtracting and it is not in the range, we term it as overflow. In this case, the result we get after adding the binary format. So now my friend Abhishek will be explaining you the solution of this question in detail.
Hi, myself Abhishek. I am going to explain you the solution of problem 1. Here we go. We have to convert x is equal. We have x, y, and z. We have to convert it into those complement. Then we have to add pairs and detect overflow. So now we start with x is equal to minus 120. So first of all, we have to take mode of minus 120, which is become 120. Now put it in binary. So we know 120 is equal to 64 plus 32 plus 16 plus 8. So we have 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. This is for 2 to power 0. 1, 2, 3, 4, 5, 6. This is for sign, which is 0 for positive and 1 for negative. Now put the values from here to here. So we don't have 2 to power 0, which becomes 0, 0. We have 2 to power 3, which is 8. So we put it 1, then 1, 1, 1. And here we got plus 120. Here is positive. So we put here 0. So now it becomes our binary number. So let's make it 2's complement. We have 0, 1, 1, 1, 1, 0, 0, 0. So first of all, we have to flip 0 to 1 and 1 to 0. So here 1, 1, 1. Now 0, 0, 0, 0. Here 1. Then we add 1 to make it 2. So 1 plus 1, 1, 0. 1 plus 1, 0. 1. 1 plus 1, 0, 1. It becomes 1, 0, 0, 0, 1. So this is our two's complement of x. Now we have to find for y same like this. So take y is equal to minus 10. Mod of minus 10 is equal to 10. We know that 10 is equal to 8 plus 2. It is 2 to the power 3. It's 2 to the power 1. So put it in 8 bits and 2, 3, 4, 5, 6, 7, 8. 2 to the power 0, 1, 2, 3, 4, 5, 6. This is for side. So we have positive, put 0 here. When we have 0, this becomes 1. This becomes 0, 1, 0, 0, 0. Now we have to, now we have 0, 0, 0, 0, 1, 0, 1, 0. So let's make it 2's complement. First of all, we have to do is to flip all zeros in one and ones in zeros. So 1, 1, 1, 1, and 4, 1, 0, 0, 1, 0, 1. This is our two's complement, 4 minus 10. Now we have to do the same. Now we have to do the same for z is equal to minus 120. Z is equal to minus 80. So we have z is equal to minus 80. So first of all, we take mod of minus 80, which is become 80. We know that 80 is equal to 64 plus 16. This is e power 4. And this is 6. Put it in 3, 4, 5, 6, 7, 8. This is 0, 1, 2, 3, 4, 5, 6 sign. We have positive, so put 0. Then we have to put it into the power 6, which is 0, 0. Then to the power 4. Sorry, yeah, but sorry, here we have to put 1 because 16 is to the power 4. Then 0, 0, 0, 0. Now we have 0, 1, 0, 1, 0, 0, 0, 0 in binary form. We have to convert it in two's complement. So we have to flip all zeros in one and all one in zeros. So first of all, we have 0. So we flip it in 1, then 0, then 1, then 0, then 1, 1, 1, 1. it is becomes 2's complement for minus 80. So now, okay, go on the next part. Here, the 2's complement for 120. Here is 2 or 1 minus 10, and here 4 minus t. Now we have case for to check the overflow. First of all, we can also check from adding x plus y is equal to minus 120, as we know that the 8-bit 2's complement overflow is in the range of minus 128 to 127, which is here we got minus 130 after adding x plus y. So this is out. This is not in this range. So it is considered as overflow, but we have to check it as binary form. So first of all, we have to take the binary of we have to take minus 120 and minus 10 into its complement, then we have to add it. So we get x 10001000. This is for minus 120. Over here for 10, it's 0. It's 1 1 1 1 0 1 1 0. So we have to add it. So 0 0 0 0 1 1 0 1 1 0 1 1 0 1 1 and here 1 1. Here we have power 0 1 1 0 and here. So here, so we have here 0 in carry in and carry out is 1. So is no 1 is not equal to 0. So carry out is not equal to carry in. So it's become overflow. So we have to do it for the next case, which is case B, in which we have to add y plus z. So we have y is equal to 1 1 1 1 0 1 1 0. Then we have to add minus 80, which we have 1 0 1 1 0 0 0 0. If we add it, so it becomes 0 0 0 1 0 0 1 0 0 0 0 0 1 1. It becomes 0 and 1 1 1 0 1 1 1 1 0 1 1 1. It becomes 1 and 1. So here carry in is equal to carry out. So carry in is equal to 1, carry out is equal to 1. So here the both are equal. So we can say that this is not a overflow. Henceforth, let's take for case C. We have case C in which we have to add x plus z. So we have we have x minus 120, which is equal to 1 0 0 0 1 0 0 0. Then we have minus 80, which is 1 0 1 1 0 0 0 0. We have to add this. So it becomes 0, it becomes 0 0 1 1 1 0. Carry in is here is 0 because there is no 1. So if we add both of these, it becomes 0 and 1. Here carry out is 1 and carry in is equal to 0. So carry in is not equal to carry out. So it is n over low. Hence proved. So we have case A is overflow, case B no overflow, and case C is also overflow.